Okay, we're gonna look at a couple of different examples here. In this first one, we've got a horizontal mass spring system. We've got a 17 kilogram mass, so I'm gonna write this down. Mass is 17 kilograms. It's pulled 13 centimeters from equilibrium. So our distance from equilibrium is 13 centimeters. And it is pulled with a force of 47.7 newtons. So this is the force of our spring, and it's released. So it's going to start oscillating back and forth. And we want to know what is the maximum velocity at which this object is going to move. So the first thing that we're going to have to figure out, well, the first thing let's do is let's convert this to meters. So we'll divide that by 100. So in order to figure out what this maximum velocity is, well, we're going to have to use conservation of energy. So at the situation in which it is fully stretched out, so let's say we've got it fully stretched out here, some mass, and let's say we've got it stretched out 13 centimeters here. At this point, we've given the system some energy. And the energy that we've given it to the system is going to be all potential energy at this point. So the energy at stage 1 is going to be potential. And if we want to figure out what the maximum speed is at, so remember the maximum speed occurs at the equilibrium point. So at the equilibrium point, let's just draw another little picture here. So at this equilibrium point, we'll try to put it in the same spot. So at this equilibrium point, well, obviously x is 0 at this point. So we don't have any potential energy left. All we have is kinetic energy. And we don't have to worry about friction. We don't have to worry about any losses of energy. So the energy at that first point, when it's fully stretched out, is going to be equal to the energy at the second point. And the amount of energy we have to start with, this is going to be the energy of the spring when it's fully stretched out, is going to be equal to the kinetic energy at the center point, the equilibrium point. Remember, spring energy can always be calculated as 1/2 kx squared, and that's going to be equal to 1/2 mv squared. So what we're trying to do here is we're trying to figure out what this v is. So first thing we can do, these 1/2s are going to cancel out because we've got a 1/2 on both sides. So we have kx squared is equal to mv squared. Divide both sides by m here. And so we have kx squared over m equals v squared. Of course, we're going to have to take square root of both sides here, which will cancel out our square root, and our squared are going to cancel here. Square root of kx squared over m. So do we know all this info, kx and m? Well, we know x, we know m. The thing that we don't know yet is we don't know what k is. So we have to figure out what k is. And remember, k was the spring constant. We can figure this out because we know that the force is equal to k times x. We're given the force, we're given the amount it's stretched. So k is going to be equal to F over x, which in this case, we're going to have F is that 47.7 newtons divided by the 0.13 meters. And if we divide these out here, we see that K, our stiffness, is 366.9 newtons per meter. And so then we can plug in all of our numbers here. 366.9 newtons per meter multiplied by X was 0.13 meters squared divided by the mass, which again was, what was the mass? 17 kilograms? 17 kilograms. So if we plug all of these numbers in here, we can see that the maximum speed that this thing is going to be moving as it passes through the equilibrium point is 0.60 meters per second. So what we did here is we said that the total energy at the start was going to be equal to the total energy at the end. The only type of energy we had at the start was potential. The only type of energy we had at the end was kinetic. If we want to expand on this, well, we can add a part B and we could say, how fast is it going when it is let's say 5 centimeters from equilibrium. And this one's a little bit trickier here because we're going to have multiple forms of energy present. So let's take a quick look at this. So the energy that we have at the start is going to be equal to the energy that we have at the end. The energy at the start, this is just the potential energy of the spring. We'll call that spring 1. And at the end, we're going to have two types of energy. We're still going to have a little bit of this potential energy left because the spring is still stretched out. And we're also going to have that kinetic energy. So remember, spring potential energy can be calculated as 1/2 kx squared. But this is the distance at the start is going to be equal to 1/2 kx2 squared plus 1/2 mv squared. So this 5 centimeters here, we're going to call this x2. So this is at the final situation. It's 0.05 meters. So again, we have to do a little bit of algebra here. The algebra is a little bit trickier here, but nothing we can't handle. So first of all of our 1/2s are going to be canceled out. And so again, we're trying to isolate this velocity here. So first thing we can do, we can subtract this kx squared from both sides, minus kx2 squared. We'll just add that over there. It cancels out here. If we want, we can factor out this k minus x2 squared. Kind of rearranged things a little bit here just to make things a little bit cleaner. We factored out that k and then kind of changed the order of them. We can divide, there we go, okay. Divide both sides by m. Cancels that out. And then we'll take the square root of both sides. So square root of k times x1 squared minus x2 squared divided by m is equal to v. And if we plug some numbers in here, we can figure out how fast the object is moving when it is 5 centimeters away. Because x1 we said was that was the original distance that we pulled it back, which was 13 centimeters or 0.13 meters squared minus 0.05 meters squared divided by this mass, which again was 17 kilograms. So you can see it's going to be going a little bit slower here because we're subtracting a little bit of this off, so 366.9 times 0.13 squared minus 0.05 squared divided by 17 and square root of that, it's going at 0.56 meters per second. So we're moving a little bit slower. Instead of moving at 0.6 meters per second, we're moving a little bit slower because there is still some energy left in the spring. So when it's 5 centimeters away from equilibrium, it's still accelerating. So by the time it gets to equilibrium, it's going to be going faster. So the key here is always kind of with any sort of conservation of energy problem, it's easiest to think about how much energy do you have at the start, how much energy do you have at the end. And in the next video, we'll look at a pendulum.